Good evening, everyone. Myself, Dr. T.R. Tamilarasan, and I'm the in charge for today's session. It is it is my pleasure to welcome you all to this AICT ATAL sponsored online FDP on AI in hydrogen and electric powered vehicles, organized by School of Mechanical Sciences, B.S.Abdur Rahman, Crescent Institute of Science and Technology. It is my honor and privilege to introduce our esteemed speaker for today's session, Professor Vasudevan Subramanian. Professor Vasudevan Subramanian is a chief scientist at CSIR Central Electrochemical Research Institute and professor at the Academy of Science and Innovative Research, New Delhi. Though his creative, interdisciplinary, and cutting-edge research, Vasudevan has made extensive fundamental and applied contributions to the field of water electrolysis, water treatment, inorganic chemicals, and storage batteries. His research has focused on novel electrocatalysts, electrolyzer, cathode and anode, electrochemical water treatment systems, anode, cathode for magnesium reserve batteries, and synthesis of inorganic oxidants. He has also been actively engaged in innovative engineering of PM-based electrolyzer, magnesium organic reserve batteries, electrocoagulation and electrofenton water treatment system, and electrolysis system for production of inorganic oxidants and chemicals. His involvement in research on electrochemistry earned his Doctor of Science degree and ranked in top 2% of scientists worldwide under Stanford University. Dr. Vasudevan has authored over 120 scientific papers and has 2 dozen of technical patents to his credit, transferred many technologies to industries, and has over 3 decades of research teaching experience in India's premier research and development institutions. Professor Vasudevan is a fellow of Royal Society of Chemistry, Australian Institute of Higher Energetic Materials, Academy of Sciences Chennai, and many other academics. He is a visiting faculty in Indian and international universities. Professor Vasudevan is one of editorial boards and associate editor of many prestigious journals, including Scientific Reports, Nature, and received numerous professional awards such as MRSI Medal. Professor Vasudevan is member syndicate and a government nominee for the officiating Vice Chancellor Madurai Kamaraj University, Madurai. With this brief introduction, I request Professor Vasudevan Subramanian sir to start the session. Today, Professor Vasudevan Subramanian will be addressing the topic of green hydrogen generation by electrolysis.
Sir, thank you very much for this nice introduction. So I thank the entire Crescent Education Trust and the people involved here, and particularly Professor Jay Kumar and Tamilarasan. Thank you very much for this type of lectures or this type of workshops are very, very important in nowadays. So now I can share my PowerPoint.
Yes, sir. Yes,
Yes.
sir. Yes.
Yeah. Thank you once again. So today I'm going to talk about the green hydrogen. That is very, very essential nowadays and talk of the town. So the title I can choose is Journey Towards Hydrogen. So nowadays, it is a colorless gold. I can say that hydrogen is the colorless gold. So secondly, in case we are not going towards the hydrogen energy, we are unable to stay in the air. Apart from there is no planet B to survive. That's why we are going towards the hydrogen journey. So the full lecture is towards the electrolysis of water, because you have to generate the hydrogen electrolysis method only. Even though there are many methods, the electrolysis is the best way to produce the green hydrogen. So why we have to make the journey towards hydrogen? So now people are talking climate risks. What is the climate risk? So the climate risk will create global warming. That means we are not make the temperature beyond 1.5 degrees centigrade of the earth. You can see that if the earth is warming beyond 1.5 degrees centigrade to 2 degrees centigrade or 2.5 degrees centigrade, there is a extreme weather will takes place. That means 170% increase in flood risk. Also, the species, you can see 18% of insects and 16% of plants and other things will be affected. And water availability is very risky. You can in 2100, if you allow the global warming, there are 410 million urban residents will be exposed to severe drought, and also Arctic sea ice melting, and people 28% of the world population will be exposed to extreme heat waves and lost their life, and sea level rise and global bleaching, coral bleaching, and also food and also the cost. So if we are not able to go with hydrogen, this climate risk will go ahead. Or otherwise, because of hydrogen implementation, you can avoid the temperature rise from 1.5 degrees centigrade and above. Normally, you can see the natural greenhouses like CO2 and CH3 will be a barrier to the earth atmosphere. So because of these greenhouse gas only, our earth is cool. That means we need the natural greenhouse gas. But in the case of human enhanced greenhouse gas only creating the problem, because the CO2 will hold the temperature and it will not release the temperature. So that's why we need the greenhouse gas, but we need not be the much greenhouse gas in the atmosphere. For example, you can see the sun energy passes through the car's window head. The heat will be inside. So that means you cannot live in the car because of the heat. So the same principle will be in the case of Earth. So here you can see the climate change is increasing the frequency and the intensity of lightning strikes and thunderstorms, which can lead to more effect in the case of the intensity of lightning. So here you can see almost 7.4 to 8 lakh people are dying in the case of the heat wave. Because of this, oxygen bar was opened in Delhi, rupees 300 rupees for 15 minutes. So we don't want to make this situation, this type of climate warming, then you have to go with the hydrogen. So you can see the surface temperature. This is the earliest since 1940. You can see the pre-industrial reference, that is 1850 to 900, 1900. You can see the 2024. We are going beyond 1.5 degrees. As I told, we should not go beyond 1.5 degrees centigrade. So you can see going on increases and decreases. Again, in the case of November month, the temperature increases 1.62 degrees centigrade because of the global warming. Even if you not obey this 1.5 degrees centigrade, there is a formation of this type of atmospheric river. If the atmospheric river happens, there is a heavy rainfall with a short time. We are experienced in India and many places this type of burst in atmospheric river and have the heavy rain in the earth. So you can see the flood was increased and forest fire will be increased and ice melting will increase and sea level will be the rise. So these are the consequences we have to face if we are not using the green or renewable energy like hydrogen. If you go for green or renewable energy, there are multiple options are there like chemical energy storage. For example, these type of batteries and advanced chemical energy storage, CO2 battery and flow batteries and gravitational energy, thermal energy and compressed air energy like that. But today I am going to talk more about the hydrogen based energy system, particularly how to produce the green hydrogen and its application. So earlier there is a fight between the batteries and fossil fuels. Now the fight between the hydrogen is fighting with batteries and fossil fuels. So why? Because hydrogen is leading is the hydrogen is the magic green fuel. It will be utilized or uses in many places of the applications. So you can see the renewable energies like hydrogen, wind, geothermal, every energies are burying the oil. So the fossil fuel industry is almost over. It is 1800 to 2024. So this is the 1956 prediction. Herbert predicted there is an oil age. It is going to be peak at 2000 and now it is declining. It is called, I can say this is the hydrogen age because we are consuming fossil fuel about 1,000,000 times more rapidly than the rate at which it was produced. So beyond 2000, we are completely going towards the hydrogen age. So this is the another typical figure. You can see the solid fuels are going on decreasing utilization and also liquid fuels also utilization is decreasing. Only the gaseous fuels will be utilized in the future with respect to the world population will be increases. These are the two graphs predicts that hydrogen and other gaseous fuels are the in the future. Supposing if you ask one question, renewable like solar and wind. So because of the drawbacks like intermediate power supply in the both cases, and in the case of batteries, how big you want and what is the capacity. There are so many questions. That's why we are going for the hydrogen energy. And also you can see the hydrogen is a multifunctional. It connects energy, mobility, and industry. So battery can't go for the industrial side. So hydrogen will be you can use for the renewable energy and also the green transport and also the industry green fuel for the industry. That's why I'm telling the hydrogen is the multifunctional. It will always connect the energy, mobility, and the industry. Scientifically, you can see that the energy density, that is a gravimetric energy density, is more. In the case of hydrogen, it is almost 142 megajoules per kg than lithium-ion batteries. You can see the volumetric energy density in the case of liquid hydrogen also more than lithium-ion batteries. You can see the scientific argument of hydrogen with batteries. Both gravimetric energy density and volumetric energy density is more. So that's why it is attractive fuel in the future. And there are many methods are available for the hydrogen production. You can see the hydrogen source is natural gas. You can produce the hydrogen or liquid hydrocarbons or the coal, biomass, biogas. So these are all the hydrogen source inputs. If you produce the method of hydrogen with these methods, you need the carbon capture systems. You can see natural gas, it needs the CCS. So in all the cases, you have to put carbon capture systems for the hydrogen. But in the case of water, you can see by electrolysis, you don't want any carbon capture systems. That's why the method of producing hydrogen through electrolysis is the green hydrogen production. You can see how much CO2 is emitted when producing 1 kg of hydrogen. You can see the gray hydrogen. If you want to produce 1 kg of hydrogen through gray hydrogen method, it will emit 22 to 26 kg of CO2 to the atmospheric. Like that blue, gray, so many colors are given based on the CO2 emission. Here you can see if you want to produce 1 kg of hydrogen through electrolysis, there is a 0 kg of CO2 equivalent. And you can see the cost-wise, there is a coal-based, natural gas-based, and green hydrogen-based. You can see the cost is almost little bit higher in the case of green hydrogen, but you can see the water consumption also less. Now the hydrogen cost is more, but because of the reduction in renewable energy, the cost is going to be less. That I can tell in the future slides. In the case of electrolysis, there are many possibilities. That is solar pathways and high temperature pathways and the low temperature pathways. If you go for solar pathways, there is a photobiological electrolysis and photoelectrochemical methods are available for the green hydrogen generation or solar thermochemical water splitting. In the case of high temperature, you can use the heat from the nuclear source. You can go for the high temperature electrolysis. But here you need the very high temperature like 600 to 1000 degrees centigrade. Here the electrolysis pathway, you can use the green energy and the temperature you record is very, very low. I can say that less than 100 degrees centigrade. So these are all the pathways you can produce the green hydrogen. So in SICRI, we are concentrating on low temperature electrolysis and few studies on photoelectrochemical water splitting. So in the case of low temperature electrolysis, there is here three types. One is alkaline, another one is PEM electrolyzer, and here is the high temperature electrolysis. In the case of alkaline low temperature electrolysis, there are two types. You can use the liquid electrolyte or the solid polymeric material. Here I can say this is called AEM electrolyzer. Here I can say this is the PEM electrolyzer. So these type of all the three types of electrolyzer we are doing in SICRI. Here you can see many parameters like efficiency, what type of electrode should be used and what type of electrolyte should be used and whether it is a commercial or it is a near-term commercial. So you can see here, these are all the three possibilities to generate the green hydrogen. But here in SOEC, you need the high temperature. In SICRI, we are not doing any research on solid electrolyte, but our sister lab, it's Glass and Ceramic Research Institute is doing this type of solid oxide electrolytes. So now we can understand, we can produce the hydrogen from the renewable source. Otherwise, it is not a green. So how to produce the hydrogen with electricity from renewables? So that is the target of the world. So renewable energy means you can use the hydropower or wind power or bioenergy or geothermal or solar power or solar thermal power. In all these are the renewable sources of energy to produce the hydrogen through electrolysis. You can make the DC to AC inverter and finally you can make all the ACs to DC converter and pass the DC converter to the electrolysis and utilize for the application side. So this graph shows the production of green hydrogen with the electricity from the renewables. There are another option of renewables, but there is no electricity. I can say that this is also called the production of green hydrogen, but there is no electricity is required, but it is a renewable. So here my point is the physicist or chemist or biologist, anyone can produce green hydrogen through their intelligence. So I can say here is without electricity but renewables. You can use the biological photocatalytic hydrogen, electrochemical photocatalytic hydrogen, biological water splitting, photoelectrochemical fermentation and conversion of biomass and waste and solar thermal water splitting. So these are all the methods. It is a renewable, it is a green method of producing hydrogen, but there is no need of electricity. So this is the eye-opening for the research scholars in any department. Concentrate on this type of hydrogen generation because India need 5 metric million tons of hydrogen in 2030. If we are not concentrating on the hydrogen, it is very, very difficult to survive in the Earth. So if you go for the electrolysis, this is the basic fundamental curve you have to understand. In the case of electrolysis, you have to pass certain voltage or electricity. Theoretically, if you want to split the water into hydrogen and oxygen, it required 1.23 volt. But it won't happen at 1.23 volt because of electrical resistance and anodic overpotential and cathodic overpotential. So these are all the factors will affect the electrolysis to produce in the lower cost. So that's why there is a fixed thermo-neutral voltage that is called 1.48 volt. So the people are trying to make the hydrogen at 1.48 volt. It is still the research is going on. If you take this graph, you can start your electrolysis research. So now I can come to the what type of catalyst are using in the electrolyzer. So I can say two types of catalyst are used in the two type of electrolyzer. One is alkaline electrolyzer or AM electrolyzer. One is acid electrolysis, or I can say indirectly PM electrolyzer. In the case of alkaline side, nickel will be the electrocatalyst in the form of porous or alloy, so many, but base is nickel. But in the case of PM electrolyzers, you can use the precious metals like platinum and the palladium. The palladium is natural choice because of the higher exchange current density and very low over potential at low current density. But the disadvantage is higher loading it required and also the high cost. The solution to reduce the cost is reduction of noble metal loadings at cathodes similar than the at anode. So we have to alternate the platinum to cheapest material, or you can reduce the content of platinum on the cathode side. So it can be reduced by using the carbon blacks with the platinum or graphene, so many things. Or the next choice is loading of platinum. So indirectly, what I'm telling it, in the case of PM electrolyzer, we are using the platinum as the catalyst. The fundamental concept is you have to reduce the platinum content in the cathode side. If you see the mechanism of electrolyzer, if it is the acid side, there is a three-step process, that is Volmer step, Iroski step, and Tafel step. So this has to follow the three steps, then only hydrogen will be formed. Suppose in the case of alkaline side, this is called in the two-step reaction, Volmer and Iroski step. So every scholars and students has to thoroughly go through this type of hydrogen evolution reaction fundamentals, then go for their studies. So you can see this is, I can say, a standard graph. So you can see here, the platinum is highest, or you can replace with, these are all the alternate metals. You can try with the platinum, with the rhodium, platinum with the iridium, platinum with the tungsten. There are so many possibilities are there. So you can take this graph and take your research. Either you can use the platinum or other metals. So the graph I can say is the volcano curve. So from the volcano curve, you can make a quick comparison of activities of different metals in the acid and alkaline media. So in the activity of HCr in alkaline media is usually lower than that in the acidic media because of the sluggish reaction of the alkaline side. So that's why you have to choose the catalyst perfectly in the case of alkaline and the acid electrolysis. So here again the OER, that is oxygen evolution reaction, takes place in the anode side. Here the overpotential loss is more, that is 40%. The HER side, the overpotential is less, but in the case of oxygen side, the overpotential is more, it is more than 40%. So now the people are concentrating more on the development of new anode catalyst to reduce the overpotential losses to 40 to 10 or less than 10%. Normally, the oxide formed on the metal surface always affect the reaction mechanisms. If you use the metallic anode, the oxide formation will be more, so the overpotential losses will be more. And the electrocatalyst for OER. Hence, the use of an oxide anode, I can say RuO2, IrO2, Ti2O2, Ta2O5, like that anodes, oxide-based anodes, that the oxide is more stable than the metal. Since the oxide cannot be easily further oxidized. So you can go for anode side, there is an oxide form of catalyst. And you can see the rutile type, perovskite type, spinel type. So these are all the possible catalysts you can go for OER oxides. You can say the rutile type is used for acid medium and perovskite and spinel type is used for the alkaline medium. From the literature, so the electrocatalyst activity will be RuO2, IrO2, like that it is going on. Now the people are concentrating more on oxygen evolution reaction than the hydrogen evolution reaction. So now what is my point of think is, now iridium is used in the anode side. There is no replacement till date. There is small group is working on many places. There is taking the some patent, but most of the people are commercial cells, iridium is used. So iridium is one of the rarest naturally occurring element. It makes up to only very less amount of iridium is available. And the catalyst made from iridium and platinum today typically 65% of iridium and 35% of the platinum. So the amount of iridium available in the nature itself very low. So the world iridium supply is currently dominated by the South Africa. You can see the price of platinum and iridium. You can see the iridium cost is going on increases. So iridium is US dollar of more than 200. Now it is almost 500 gram. So this is the price of metal, and the global annual production is only 7.5 tons. So if we are targeting big type of electrolyzer, we need 20 tons of iridium, but availability is only 8 tons of iridium. So we have to go non-iridium based catalyst in the future. So this is the one thought everybody has to keep in mind, that if you are going to work in PEM electrolyzer, in the case of anode, in the case of cathode, you have to replace with iridium and the platinum. So these are all the countries making the resources in India. So there is no resources, very less resources available in India. But in the case of African countries and other countries, the resources are more. So we have to target the Indian market with respect to availability of catalyst or availability of metals available in the India. So these are all, how to choose the electrocatalyst. I can say that the design flow diagram, you can identify the target reaction, whether you want HER, you want OER or NRR. So many you have to identify, then choose the suitable catalyst, and take the optimization and surface modification. And this is the route path for the selection of electrocatalyst, either in the cathode side or the anode side. Finally, it is a environmental friendly and economically consideration. Why I am saying the environmentally? Sometime if you use cadmium, so it is not a environmental catalyst for the green hydrogen. So it is a environmental and economical consideration will be taken. So apart from these catalysts, there is another part is current collector. In the case of hydrogen side, the electrode potentials are close to zero. So it is possible to use the carbon-based materials such as carbon papers and other things. But in the case of oxygen side, you cannot use the carbon-based material because of the carbon corrosion will be the takes place. So this is the big research for the mechanical engineering department, because they have to make the proper current collectors to replace the carbon porous titanium structure in the case of PM electrolyzer. So the chemistry can take place in the case of anode and cathode catalyst. The mechanical department can take the challenge of this type of current collectors. So you can see the PM electrolyzer, it started in 1970. It is step by step, it is going on now. It is 2020 kilowatt, megawatt and gigawatt scale is now started, because of we need more green hydrogen. We have to go to megawatt scale. So the fundamental is, here is the proton exchange membrane electrolyzer. So here SICRI is concentrating more on PM electrolyzer. This is the membrane where I can say the water will be split into the oxygen and the hydrogen side. Okay, the electrolyte, I can say the proton exchange. This is the solid electrolyte we are using, and water is the reactant where noble metal is used, hydrogen and oxygen will be evolved. In SICRI, we have made several examples. I can say more than 1,000 catalysts we prepared based on the carbon, and finally we optimized with the carbon based platinum. This is the one type of catalyst developed, patented by the SICRI, and another one is the platinum, to how to reduce the platinum content in the cathode side. This is the typical method we are using by the deposition method. How much platinum is required? So based on the performance, we can reduce the platinum content through the deposition method. So in the case of oxide side, we are still using the IRO2 based system only. I can proudly saying that still we are struggling to replace the IRO2 based catalyst, but slowly we will go to less IRO2 based the catalyst. So this is the first prototype developed in the year 1996 to 2000. So it will generate only the 0.02 meter cube of hydrogen. So here you can see there are membranes and both anode side and cathode side. As I said, these are all the current collectors and current distributors. So very compact electrolyzer cell. Even though the green hydrogen concept was started, we are started in the year 1996 itself. So this is the first green hydrogen prototype model developed in SICRI in 2000. So we made several performance like current voltage and how much duration and going on. Apart from the knowledge based on the 0.02, we are gone to little bit higher. We are also successful in this also, and still we are gone to 0.8 nm cube. Here also we made the successful, and we gone for the complete system. Here this is 1 meter cube of hydrogen where it can produce 1,000 liters of hydrogen through PEM electrolyzer. Earlier we made small things. Now we can able to make bigger size of systems. In the case of PM electrolyzer, we have a lot of students to working on this project. So apart from that, we are also made a separate cells for 2,000 liters and 3,000 liters, 4,000, and finally now in 2024, with great difficulties, we are able to do 6,000 liters of hydrogen. Our future within 2 to 3 years, we are planning for the 20 to 25 nm cube of hydrogen. We are getting the project from CSR and MNRE for the higher scale studies. So these are all the technical specification. We are on par with the international market. So the thing is, once you developed means you cannot keep the technology with itself. So during the year 2012, we are transferred this PM electrolyzer to the Eastern Electrolyzer Company. So I am happy to share that we developed the technology, we transferred to the one company, and they are making the electrolyzer, and they are keeping the cells in many places like Oman, and VRC, they are started producing our own technology. Now we are utilizing our electrolyzer using the solar as the energy source, because if you are not generating the hydrogen through solar, it is not a green energy. We have started working on solar based hydrogen energy. Still we have the R&D focus will be there in design of membrane, catalyst, durability. There are so many R&D focus is needed to achieve the target of 2050. So Department of Energy, DOE, is given the target of very high target to achieve in 2050. SICRI is going towards the 2050 target. So these are all the some of the R&D progress. We are making the sacrificial coating of platinum on membrane. We are going for the in situ deposition to reduce the IRO2 concentration. We are going for the indigenous available membrane. So many type of R&Ds are going on to reduce the cost and to meet the target of 2050. So I am happily say that SICRI's technology is competitive with the all over the world. These are all the competitors available in world, and we are also one of the competitor in the world. So here is the overall system, PM supply chain. Here suppose if you want the green energy system, this is not a single man army. We need the electrical engineer, we need the electronics engineer, we need the physicist, we need the chemist, and we need the biologist, because it is a complete system. It is having the electrolyzer stack and deionized drinking and water treatment and cabling, hydrogen water separation, piping, cooling. So it is the integration of all the departments, like the private university have all the departments. So if you concentrate all the departments and sit and work on that, definitely that the India can go for this type of electrolyzer systems. So another type is alkaline water electrolysis. As I said in the earlier, this is the PEM and alkaline electrolyzer. Here we are using the 30% of KOH. There we are using the only water, membrane is the electrolyte. Here we are using the only separator, and we are using 30% of KOH. Here is the very old, 100 years old technology, but now we are improving the 2050 target. So these are all the different electrode coatings are available in the preparation of alkaline electrolyzer: electrode deposition, thermal spraying, hot pressing, sandblasting, PVD, hot dipping. So I can suggest anyone is in your universities expertise in this case, they will contribute in the electrode coating of alkaline electrolyzer. You can say you can use the pure nickel means, as I said, you can get the efficiency of 72.5. You can go for the alloying, that is Raney nickel, still the efficiency will be more, and Raney nickel on cathode and anode, you can see. So this is the progress. We need this type of progress for the alkaline electrolyzer. So before going for the pilot scale, you have to do the many fundamentals like galvanostatic and cyclic voltammetry, linear sweeping voltammetry, impedance studies. So if you want to develop the catalyst, you have to go for this type of characterization. And the question is whether nickel is available means yes, you can, plenty of nickel is available. That's why now the world is concentrating on alkaline electrolyzer rather than the PEM electrolyzer. You can see the comparison of alkaline, PEM and SOEC. Today you can see the energy is 48 and the PEM is 56 and the SOEC 41. Ultimately, the alkaline electrolyzer having little bit energy and the cheap, and lifetime stack or lifetime also increases. You have to, if you are interested, you can concentrate alkaline electrolyzer using the 30% of NaOH. And another question is whether water is available for alkaline. Even in the case of many hydrogen production systems, water is needed. Like that, you need water for the hydrogen system. Enough water is available for the electrolysis of water. So initially, in the case of alkaline electrolyzer, we developed only the electrode rather than the electrolyzer. After the development of indigenous electrode, immediately the technology was transferred to the existing electrolyzer manufacturer. Then we started our own electrolyzer system with many components. We developed the 5 kilowatt system as a demo model, and now we are going for the 50 kilowatt alkaline electrolyzer. Like PM, here also we need the entire system like balance of plant and the electrolyzer. Here also the same concept of all the engineers and scientists will work for this type of systems. Here we are not at all working in high temperature electrolysis. As I said, here we need the high temperature, that is, if it is a waste heat is available, then you can go for the high temperature electrolysis. Here also same. So you can see the timeline. We can started in 1996. We are slowly developing in 2012, 2015, 2022, and 2030s. We are going to meet the India's requirement of 5 MMT of green hydrogen. So this is the timeline. It is not just like that we started this work. It is a 30 years of work we are done in the PM electrolyzer system. Apart from this PM, we are also concentrating to replace the 30% of KOH to the alkaline anionic chain membrane. Like PM, here also you can use the AM, you can use the water, and also we are also making the direct seawater electrolysis. Suppose if plenty of seawater is available, we are now SICRI is concentrating this type of new system for the hydrogen generation. So you can generate the hydrogen from the seawater, either desalinate or you can use the direct seawater. So if you want to use the seawater, so the chlorine is the main problem. So you have to avoid the chlorine evolution, the anode side. So this type of approach for the seawater electrolysis going on. So if you use the seawater, only chlorine. This is not a environmentally friendly technique for the utilizing the seawater for the electrolysis. For that, we are concentrating to replace the chlorine evolution and make the oxygen evolution takes place in the seawater electrolysis. We are making many research based things. We are publishing many papers, and almost we are achieved 90 to 100% of oxygen evolution takes place, and we are decreased the chlorine evolution to almost zero. We are successful in the case of seawater electrolysis. And as I said, if you want to replace the precious metals, we are also going for the non-noble metal catalyst and also the photoelectrochemical generation. So here is the typical example. As I said, this is the eco-friendly method of preparation of TiO2, SiO2. So you know that the sandblasting machine. So everybody we know the sandblasting machine is used for only to sandblast the metals. We used the sandblasting machine to make the new catalyst. You know that more silicon will be available in the sand. So, and the high temperature, SiO2 will be formed. So, the base metal is the titanium. Okay. If you use the high, in the case of the point, the temperature is very high. When we are analyzing the plate, there is a catalyst called TiO2, SiO2. So, very simple process and novel process. You can make this type of method to produce the TiO2, SiO2 cathodes. Like that, we used the alumina as the source. In the place of sand, if you use alumina, you can get the TiO2, Al2O3 catalyst. This is also another method of invention and non-noble catalyst. So we are going on trying this type of new methods and new catalyst for the photoelectrochemical process. Here we are also trying for the carbon and nitrogen co-doped TiO2 photoanodes. That is non-metallic TiO2 photoanodes. Apart from the electrolysis method, as I said in the previous slides, we are also concentrating on alternate methods like seawater electrolysis and AM electrolysis, and also completely replaced the entire system to photoelectrochemical methods. So like iron oxide TiO2, Al2O3 TiO2, there are many methods are available to prepare like this. For example, you can see, as I told in earlier cases, India is rich with iron. So you can go for ferrite, iron-based catalyst for the alkaline side. So I can say that calcium ferrite, cobalt ferrite, like that there are many ferrite, iron-based catalysts are now booming in the Indian side. So that you cannot depend on other countries for the iridium and the platinum. So in that angle also, we are proceeding towards our research. So one novel method is we are making the electrochemical tuning of TiO2. So that is the cathodization. So that we achieved nearly the LSV nearing to the platinum. So this is the one of the method we are making the cathodization of TiO2 and we are achieving the very close to platinum. So this type of advanced research is going on. Apart from that, the SO2 electrolysis, you can get the hydrogen and sulfuric acid as the byproduct. So here is the world is many companies are started in the alkaline and PM electrolyzer. So whenever you go for the new systems, there is a danger. So if you use the hydrogen system, there are many places accidents or takes place. You have to more careful on that. You can see the utilization point of view. Here you can see the long term and it is used immediately. So you can see the industries. Those industries are immediately using hydrogen and those industries are expected to use hydrogen in the future. So the Indian and world countries are started utilizing hydrogen to use. You can see the steel and shipping and fertilizer, aviation industries are going on using the utilizing. So somebody will take that use of green hydrogen would have a significant impact of the price. But impact on intermediate product US dollar is less. But if you go for the impact on end product is very less. In the case of any industries like steel, shipping and other things, the impact of cost will be very less. This is the study taken place in the many places. You can see one example, fertilizer produced using clean hydrogen at $0.5 kg. So the impact is minus if you use the Haber process. If you use the fertilizer, in the case of ammonia fertilizer, the impact is less. So this is the concept we want. We want the hydrogen production in the less price so that impact will be the negative side. So now the people are going towards the negative impact side. You can see the gaseous state and liquid state, the cost example, the TRL level. These are all the storage concept. Suppose if you want to store, the TRL level is 9 in the case of gaseous states and liquid state and solid state. So if once it produced, you can go for the storage. There are so many methods of storage is available. And now I can come for the general and future viewpoint of hydrogen. Already the world, China started the commercial fuel cell powered long line in China. And the zero avia is already started for the aviation. In 2040, there are 200 plus seats of zero avia, that is zero carbon aviation will be available in 2040 to 2050. The thing is, we want a more space to accompany this type of hydrogen systems. And the Berlin was already started the Berlin airport with the complete hydrogen system. You can see the electricity, hydrogen generation system, hydrogen storage system, and also getting the electricity from the fuel cell to the grid. So this is the concept already started many places. The airport is zero CO2 emission. Even in the aircraft and the airport, there is no CO2 emission in the air. That's why this is the way you have to reduce the surface temperature to less than 1.5 degrees centigrade. The hydrogen powered houses are started. Even the hydrogen based engines for aircraft was started. And you can see the confidence in role of hydrogen and readiness level. You can see that aviation and shipping steel are the confidence level is little bit higher. But in the case of confidence level is lower means heating purposes and you can generate the plastics, right? These are all the people is a ready or lower confidence level rather than the higher confidence level. I can say the confidence level is more in the case of fertilizer in the production of methanol and refining, but the confidence level is less in the case of many places. And this is the cost, capex cost of electrolyzer, both historical and projection for alkaline electrolyzer. So the cost of capex, the capital cost is going on decreasing in 2035. The capex cost will be very low in the case of all electrolyzers. So here the size of individual electrolyzer plants are commercialized. It is going on increasing. You can see the electrolyzer megawatt. As I said, we want the megawatt electrolyzer. You can see in the 2020, the megawatt work is started. In 25, in 30, you can see 1000 megawatt and 10,000 megawatt of electrolyzer will be available for the generation of green hydrogen. The cost is, you can see now in 2020, the cost is little bit higher. And in due course in 2030, we are expecting the cost is 3 euros per kg. And you can say in 2040, I can say that 1 euro or $1 of hydrogen per kg all over the world. In 2040, the cost will be less than the carbon-based, coal-based fuels. In 2050, almost all countries will produce the hydrogen in the lower cost. You can think that it is possible to reduce the cost of hydrogen very easily? No. Suppose you can take the example of 4.9 US dollar per kg. Suppose I want to reduce at least $1 means 3.9. I have to concentrate on electrolyzer efficiency and decrease of cost of renewable power and capex and increase in the life of the electrolyzer and decrease the operating and maintenance. So I have to take care of these things. Then only if I can reduce 60%, 50%, 0.9, so I can reduce only $1 per euros. So we have to be concentrating. If you want to make $1 per kg, you can assume that how much work you need. Suppose if you want 1 metric ton per year means you need the 10 gigawatt of electrolyzer and you need the 20 gigawatt of renewables and you need the investment of $30 billion. That is 1, 10, 20, 30. You can keep it in mind. We want to reduce this 30 to less than 20 like that. So the challenge is you can use the hydrogen in the cement industries. So you can see this is a normal conventional process. Here it is, you can use the hybrid electrolyzer so that you can get the concentrated CO2, then you can recover easily. For that, you want the hybrid electrolyzer. This is the new concept. You have to work on hybrid electrolyzer. One side you can use oxygen and CO2 will be come out, but in the case of cathode side, hydrogen will be come out. So here the new system is called hybrid electrolyzer, mostly for the cement industry. This is the one target given to everyone all over the world. You can go for this type of hybrid electrolyzer. The another one is the Haber process. We know that ammonia is produced by the Haber process. These are all the hydrogen production method in the Haber process. Suppose if you make the electrolyzer here, you can see how simple you can make the green ammonia. You can use this type of electrolyzer and you can nitrogen produced by the air. Just you can pass the hydrogen to the system, you can Haber process reactor, you can get the ammonia. So only thing we have to reduce the cost here so that the CO2 emission and the cost will be reduced. You can see the cost or CO2 emission will be very, very less in the case of ammonia production through green hydrogen systems. Like steel industry, you can see the blast furnace producing the CO2. The alternate method is you can go for the hydrogenation process or you can go for the electrochemical process so that you can avoid the 2 tons of carbon dioxide, because if you want to use 1.6 tons of iron ore to produce 1 ton, you are generating the 1.9 tons of CO2. If you avoid this type of CO2 emission, you can go for the utilizing the green hydrogen to the hydrogenation process. As I said, this is not a very, very simple process. You need the fluid mechanics research, chemical research, and material science research, and also the electric and electronics people. So all this type of integration is required for the green hydrogen in the world. So now India is started to make the India Hydrogen Valley. Here we are making the hydrogen from renewable and making the hydrogen through electrolysis and storing, and also during we are making the pipeline, what is the cost and other things, and utilizing. So this type of hydrogen valley is already started through India, particularly in the case of Varanasi and many places. This hydrogen valley is started, and SICRI's contribution in the valley in the production side. So you can see almost 1,600 kg capacity hydrogen was started in Silicon Valley in 2021. Now in 2024, there was in 3,000 kg of capacity station was started. So the hydrogen economy challenge is marketing challenge, technological challenge, fuel processor, safety management is very, very important, and regularity and stationary approval. So now I can come to hydrogen energy in India, in what way and how to proceed India in the hydrogen. So we are going towards the Viksit Bharat at 2047. As our Prime Minister told today, the goal of the country is Viksit Bharat. We cannot stop until this dream of the developed India in the fulfilled. So you maybe know that India International Science Festival 24 is going on. So the transforming India into a science and technology driven and global manufacturing hub. So in this concept of Viksit Bharat at 2047, the green hydrogen concept is going on India. Already is the national India's green hydrogen mission was started. They are given almost 20,000 crores of rupees for hydrogen. That is given for many disciplines. For in the case of R&D also, they are given the plenty of rupees for this type of green hydrogen mission. Already the commercial scale green hydrogen, clean hydrogen production was started, and L&T, Reliance, Indian Oil, Chennai Petroleum Corporation, Greenco, GAIL, Bharat Petroleum, Fusion Fuel, and many industries are started for the green hydrogen product. With these industries, SICRI is collaborating for the many places. So I can say that very recent notification, it was 2 days back. So MNRE is given the orders to these industries to produce this type of metric tons of hydrogen per annum through green hydrogen system. This will show that India is going towards the climate change and the climate concept and towards the green hydrogen manufacturing system. You can see the hydrogen demand in India is expected to increase at a faster pace due to the new area. That is, we are expecting, India is expecting 16 to 20 MTPA by 2040 towards the ammonia industries, refineries, and many places. The hydrogen will be used, and the compound annual growth rate also increases from 4.2 to 16 MTPA. So now you can see the Uttar Pradesh and Gujarat are expected to be the key hydrogen consuming state. The presence of current and upcoming refineries and ammonia and urea in Uttar Pradesh and Gujarat, and strong chemical belt in Gujarat potentially consuming more hydrogen. Apart from these Gujarat and hydrogen, you can see all other states also making use of hydrogen in their states. You can see we need the renewable capacity to produce the green hydrogen. You can see in 2023, almost 172 gigawatt of renewable hydrogen was started. We want 100 gigawatt of energy to achieve the 46 gigawatt of electrolyzer. So, in parallel, we are making the renewable energy and also the hydrogen energy systems. You can see once again, I am telling that water requirement to meet 5 metric ton of hydrogen target is, there is no water scarcity in India to make to or achieve the 5 metric ton of hydrogen in the 2030. You can see the green hydrogen versus gray hydrogen cost. You can see the Niti Aayog given a target of $1.5 per kg, but we are here 2.34, but Indian Niti Aayog will given 1.2 or less than US dollars per kg of hydrogen at 2040. But because of their renewable energy, the cost is going on decreasing. This will show the positive sign of green hydrogen generation in the cheaper cost. And you can see considering the carbon pricing and the MNR incentives, you can see the cost will be still less in the case of blue hydrogen. If you give the incentives or carbon credit, so ultimately the hydrogen production cost. This is also the prediction that we are going on decreasing the cost. So suppose if green hydrogen mandates in refineries, is there any price increase in the petrol price? For this contrast, so at 50% green hydrogen mandates, the price of petrol may rise from rupees 100 to, this is for example, I can saying that 1 or 2 to 4. Only the increase is very, very minimal. That is, I can say that 2.5% only increase. If you are mandate is green hydrogen to the natural gas or petrol, the cost will be low. But in the case of ammonia production, we need the government support will be required in the case of ammonia production. But transporting hydrogen through pipeline, and you can see there are two graphs. So the lower capacities transport by road is more economical, but for higher capacities, pipeline is more economic. So these type of researches also going on in the transportation sector. You can see that these precursors have been mapped with the existing refineries like Gujarat, West Bengal, Andhra Pradesh, and these type of seashore states are very well in the case of hydrogen demand. Why I said in Gujarat means this is the biotech cluster, and engineering and ceramic and chemicals and petroleum and pharma. These are all the clusters of more industries are available in the case of Gujarat. That's why I'm saying Gujarat is more demand of hydrogen rather than the other state. In the case of Indian Railways, the Indian Railways, one of the biggest train network worldwide, transport over 24 millions of passenger and 3 MT of freights daily. So now the hydrogen for heritage, this is the concept already started. So you can see the cost wise, I can compare here you can see diesel train, electrified line, battery train and hydrogen train. You can compare everything. So the capex, hydrogen and diesel and electricity, you can compare everything. And finally, you have to come for the emission. Here you can see almost 900 tons of CO2 per year. So you can see if you use hydrogen train, the carbon emission is very, very less. Even though the cost and other things are here and there, so the final is 6.5. Overall, the fuel cost saving are expected in the case of any electric train is 12.5 crore. Compared with the hydrogen train, it is 22 crore. So here I can happily say that the hydrogen trains are giving only low hydrogen emission. And there are many challenges and opportunities for the green hydrogen. I can say the initial cost is high and safety precautions and heavily rely on the green hydrogen imports. So advantages and opportunities more rather than the challenges. Already India started, India's first hydrogen CNG station was started, and the hydrogen CNG filling station in India was started. There are many things was already started. In CSAR SICRI, we are made hydrogen-based cars and hydrogen-based buses utilizing the hydrogen-based fuel cell and also the electrolyzer. So come to the final, I can say that still date, till now, I can say the normal chemist. So I can see in the environmental chemist whether the hydrogen will give the warming effect. I can say that hydrogen is also giving to the warming effect in the atmosphere because of the leak. So you can see in the production there is a leak, and compression and storage there is a possibility of leak, and distribution there is a possibility of leak, and application there is a possibility of leak. So hydrogen is a leak prone gas that leads to potent climate warming in the near term. So it is not necessary that if you produce the hydrogen and you are assuming that it will not given the heat. But if you are not following the certain norms, I am sure that hydrogen also giving the warmth, because it will also react with the OH ion to produce methane and also the ozone. So in the high altitude, the water will be increasing. So that means, as I said, in the atmosphere, river will be formed. So you have to take precautions when you are producing, when you are utilizing, when you are transporting. I am sure that hydrogen will not produce warming effect, but it will produce the warming effect when you are careless. So as an environmental scientist, I can argue that hydrogen is warming. As a scientist or a general scientist, I can say that hydrogen is the non-warming the method. So there is a conflict between environmentalist and the energy scientist. So the warming effect will be takes place. So with this, I can end that there is a quote in 1874. I believe that water will one day be employed as fuel, so that hydrogen and oxygen, which constitute it, used singly in the case of system or together in the case of fuel cell, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. So Jules Verne is given this statement in 1874 Now we are realizing. So I am telling in 2015, water will replace the fossil fuels as the primary resource for the hydrogen. So this is the last slide. I have given the full, my lecture is based on the technology. So the crossing the valley to depth, from fundamental to applied research or developing the technology is not so easy. So from this is a fundamental, this is to where we are going. It is, and you are thinking that this is easy. No, you have to this academic research to industrial research. You have to cross this valley of death. I can say in the case of catalyst or in the case of electrolyzer, you can see the catalyst screening, benchmark systems, measurement of protocols, report of results. There are plenty is available. So I can say that if you want to make the industrial research, you have to cross this valley of death. You can keep it in mind. Everyone, it is not so easy to develop for the industrial research, for the, for the technology. So this is my last slide. Very much thank you for your listening. Thank you very much for this opportunity.
Any questions from the audience?
One question, sir, one question from Mr. Jayavelu.
Yes.
Professor, I am beginner. Where can I start from hydrogen research?
So my answer is you can start. I don't know whether in which area, whether he is a mechanical engineer or chemist or physicist, biologist, I don't know. But in their field, they have to read more on electrolyzer or hydrogen research where they can fit. In the case of electrolyzer, they have to start with the catalyst and also the many components are available. So depending upon the field, they can start the hydrogen research. I can, in the case of mechanical engineering, I can say that here is the current collector bipolar plates are very, very important. Still the people are using titanium and stainless steel, this type of metals are used in the electrolyzers. But if as a mechanical engineering, you can go for the composite, less weight, but the electrical conductivity is equivalent to metallic. So this way I'm telling your technology is very, very difficult. If you are able to make this type of composite material equivalent to metal, so it is very, very useful for the electrolyzer, as in the case of mechanical engineering department.
Sir, one more question from the audience.
Electrical engineering.
Possibility research in hydrogen generation from electrical engineering field.
Yeah, here I can say the I told no balance of plant. Apart from electrolyzer, there is a balance of plant is required. Here we have to make sure that the rectifier efficiency will be the less, or you can make wiring and everything will be very, very important. And at the same time, as I told in the mechanical engineering, the composite material also very much interested in the electrical, because we need the electrical conductivity is equivalent to the metals. So many places the electronics and electrical engineering is very, very important in the case of development of balance of plant.
So thank you so much, Professor Vasudevan Subramanian, for that insightful and enriching session. Your talk on hydrogen generation has been truly enlightening. On behalf of everyone here, I would like to express my sincere thanks for the valuable information and insights that you have shared with us today. Once again, on behalf of organizers and BSA Crescent Institute of Science and Technology, thank you, Vasudevan sir, for taking the time to be with us today. Thank you, everyone.
Thank you.
Thank you. Thank you.
Very much, sir.
Thank you very much, sir.
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you.